Lecture 1. VSEPR theory explains why molecules have specific shapes. The main idea is that electron groups around a central atom repel each other. Because they repel, they arrange themselves as far apart as possible. This helps minimize repulsion and make the molecule more stable. A single bond counts as one electron group. A double bond also counts as one electron group. A triple bond also counts as one electron group. A lone pair also counts as one electron group. But lone pairs repel more strongly than bonding pairs. So when lone pairs are present, they can change the bond angles and the final molecular shape. The key idea is this. Electron groups arrange themselves to minimize repulsion and maximize separation. Lecture 2. Basic molecular shapes depend on the number of electron groups around the central atom. If there are two electron groups, the shape is linear. In a linear molecule, the electron groups are 180 degrees apart. Carbon dioxide is a good example. The carbon atom has two electron groups, so the molecule is linear. If there are three electron groups, the shape is trigonoplanar. The bond angle is 120 degrees. Boron trifluoride is a good example. If there are four electron groups, the electron group geometry is tetrahedral. The ideal bond angle is 109.5 degrees. Methane is a good example. The key idea is this. The number of electron groups determines the basic molecular geometry. Lecture 3. Lone pairs change the shape of a molecule because they repel more strongly than bonding pairs. A lone pair takes up more space around the central atom. Because of this stronger repulsion, bonding pairs are pushed closer together. That makes the bond angle smaller. Ammonia, NH3, is a good example. Nitrogen has four electron groups. 3 are bonding pairs, and 1 is a lone pair. So the electron group geometry is tetrahedral, but the molecular shape is trigonopyramidal. The bond angle is about 107 degrees. Water, H2O, has 4 electron groups too. But oxygen has 2 bonding pairs and 2 lone pairs. Because there are 2 lone pairs, the bond angle becomes even smaller. Water has a bend shape with a bond angle of about 104.5 degrees. The key idea is this. Lone pairs compress bond angles and change the molecular shape. Lecture 4. When a central atom has 5 electron groups, the basic arrangement is trigonobipyramidal. This arrangement has 2 types of positions. Equatorial positions are 120 degrees apart. Axial positions are 90 degrees above and below the equatorial plane. If all 5 electron groups are bonding groups, the molecular shape is trigonobipyramidal. PCl5 is a good example. If there are 4 bonding groups and 1 lone pair, the shape becomes seesaw. SF4 is a good example. If there are 3 bonding groups and 2 lone pairs, the shape becomes T-shaped. ClF3 is a good example. If there are 2 bonding groups and 3 lone pairs, the shape becomes linear. I3- is a good example. The key idea is this. 5 electron groups start with a trigonobipyramidal arrangement, and lone pairs change the observed shape. Lecture 5. When a central atom has 6 electron groups, the basic arrangement is octahedral. In an octahedral arrangement, the bond angles are 90 degrees. If all 6 electron groups are bonding groups, the shape is octahedral. SF6 is a good example. If there are 5 bonding groups and 1 lone pair, the shape becomes square pyramidal. BRF5 is a good example. If there are 4 bonding groups and 2 lone pairs, the shape becomes square planar. XeF4 is a good example. The important point is that lone pairs usually take positions that minimize repulsion. In the square planar shape, the 2 lone pairs are opposite each other, so their repulsion is reduced. The key idea is this. 6 electron groups start with an octahedral arrangement, and lone pairs can produce square pyramidal or square planar shapes. Lecture 6. To predict molecular geometry, follow a clear method. First, draw the Lewis structure. You need to show the bonds and any lone pairs on the central atom. Second, count the electron groups around the central atom. Remember, a single bond, double bond, or triple bond each counts as 1 electron group. Each lone pair also counts as 1 electron group. Third, count the bonding groups and lone pairs separately. Bonding groups are atoms bonded to the central atom. Lone pairs are non-bonding electron pairs on the central atom. Fourth, match the pattern to AVSEPR geometry. For example, hydrogen sulfide, H2S, has sulfur as the central atom. sulfur forms 2 single bonds to hydrogen and has 2 lone pairs. That gives 4 electron groups in total. There are 2 bonding groups and 2 lone pairs. So the electron group geometry is tetrahedral, but the molecular geometry is bent. The key idea is this. Draw the Lewis structure first, then count electron groups, bonding groups, and lone pairs. Lecture 7. Bond angles become smaller when lone pairs are present. This happens because lone pairs take up more space than bonding pairs. The strongest repulsion is between 2 lone pairs. The next strongest repulsion is between a lone pair and a bonding pair. The weakest repulsion is between 2 bonding pairs. Methane, CH4, has 4 bonding pairs and no lone pairs, so it has the ideal tetrahedral bond angle of 109.5 degrees. Ammonia, NH3, has 1 lone pair. That lone pair pushes the bonding pairs closer together, so the bond angle decreases to about 107 degrees. Water, H2O, has 2 lone pairs. The 2 lone pairs repel even more strongly, so the bond angle decreases further to about 104.5 degrees. The key idea is this. As the number of lone pairs increases, bond angles usually decrease. Lecture 8. Bond order helps us compare bond strengths, bond energy, and bond length. A single bond has bond order 1. A double bond has bond order 2. A triple bond has bond order 3. As bond order increases, the bond becomes stronger. That means the bond energy increases, but the bond length decreases. Single carbon-carbon bond is the weakest and longest. A carbon-carbon double bond is stronger and shorter. A carbon-carbon triple bond is the strongest and shortest. This happens because multiple bonds have more shared electron density between the 2 nuclei. That stronger attraction pulls the atoms closer together. The key idea is this. Higher bond order means higher bond energy and shorter bond length. Lecture 9. Dipole moment measures the separation of positive and negative charge in a molecule. A molecule can be polar only if 2 things are true. First, it must have polar bonds. Second, the molecular geometry must not cancel the bond dipoles. CH3Cl is polar. The carbon-chlorine bond is strongly polar because chlorine is more electronegative. The molecule is not perfectly symmetrical, so the bond dipoles do not cancel. The net dipole points toward chlorine. CCl4 is different. Each carbon-chlorine bond is polar, but the molecule is tetrahedral and symmetrical. The bond dipoles pull equally in different directions, so they cancel each other out. That makes carbon tetrachloride nonpolar. The key idea is this. Molecular polarity depends on both bond polarity and molecular geometry. Lecture 10. Hybridization connects electron groups with orbital arrangement. If a central atom has 2 electron groups, it usually has sp hybridization. This gives a linear arrangement. If a central atom has 3 electron groups, it usually has sp2 hybridization. This gives a trigonal planar arrangement. If a central atom has 4 electron groups, it usually has sp3 hybridization. This gives a tetrahedral arrangement. Now let's connect this to sigma and pi bonds. A sigma bond forms by head-on overlap of orbitals. A pi bond forms by side-by-side overlap of orbitals. Every single bond is 1 sigma bond. A double bond contains 1 sigma bond and 1 pi bond. A triple bond contains 1 sigma bond and 2 pi bonds. For example, ethene has a carbon-carbon double bond. That double bond contains 1 sigma bond and 1 pi bond. Ethene has a carbon-carbon triple bond. That triple bond contains 1 sigma bond and 2 pi bonds. The key idea is this. Hybridization predicts orbital arrangement, and multiple bonds contain 1 sigma bond plus 1 or more pi bonds.